time domain now. And so the questions then arise, what do the eigenvalues of this composition operator look like? And how do they depend on the size of the time and frequency supports? And how do they depend on the linear distribution of the frequencies? Especially I'm interested in the case where the time support is simply an interval, but the frequency support is finite unit. And so the more interesting stuff that I may not get to has to do with time localized approximations of signals that are in the image of this operator, P signal, Q S, P signal, that are, well, that are in the image of large eigenvalues, that are in the eigenspace of large eigenvalues. And how can we recover signals like that from samples? So phi n are eigenvectors. So that means quantify the projections onto the eigenspaces in terms of samples of the function. And in practical terms, find finite dimensional approximation. And then this is all we're talking on the real line, but in real life we have to work with data and use FFTs and stuff. And so what issues arise there? So a quick review of the Bell Labs theory from the 1960s. This is the case in which the frequency support is one interval. So we're just talking about the Bailey-Wiener space that Yuri mentioned at the beginning of this section. Okay, so this operator, this composition of the projection onto the Bailey-Wiener space, followed by the time localization, and then the projection back onto the Bailey-Wiener space. Self-adjoint, and if these sets have finite measure, then the operator is compact. We can order the eigenvalues in decreasing order, and the maximum eigenvalue is the suit of the time localizations of the functions of the Bailey-Wiener. And the uncertainty principle simply says that this maximum eigenvalue is less than 1 if the sets have finite measure. So the classical case is both the time and frequency supports are intervals. In this case, the trace of P omega, I'm calling it now, Pt, is the time frequency, the area of the time frequency problem. And the orthonormal eigenfunctions I'm writing as in this manner. And well, the so-called lucky accident is that P omega Q2 commutes with this differential operator whose eigenvalues are known. Whose eigenfunctions are known to be the correlated spheroidal wave functions that arise in physical applications. And so the eigenfunctions were understood because people had written long, voluminous books with tables of their values, and before we had computers. And so everything was understood about the case in which the time interval and the frequency, the time support and frequency support are both intervals. So everything was explained in several papers by Landau, Slepian, and Pollock in 1960. And the eigenvalues are approximately the time frequency area omega t, eigenvalues close to 1. The eigenvalues then plunge over a region with approximately the log of the area, and there's a transition around an eigenvalue of 1/2. So the next eigenvalue, the area plus 1, is less than or equal to 1/2, and the area minus 1 is bigger than or equal to 1/2. And that particular result did not appear actually until 1993 in a paper by Landau, although I'm sure that he knew it previously, and there were estimates where this 1/2 was replaced by a smaller number here, and a bigger number in the late 1960s by Landau as well. So he had thought about this for a long time. So this is just an illustration of the eigenvalues with 128 point discrete Fourier transform. And the area here, now you can't talk about area in the same way as on the real line, but you can talk about normalized area. So that means the number of time points times the number of frequency points divided by n. Okay. In this case, it's 8, and you can see that there's an eigenvalue of a transition around around lambda equals a half, and this one's 7 and this one's 9. And those are the corresponding eigenvectors, and you can see that the first few are localized close to the center, and then they start getting spread out as the index gets larger. And once you get past an index of 8, more than half the energy is outside. Now you can start experimenting with multiple frequency intervals, and that's what the spectrum looks like. If I take 129, I don't want to go into why I have 129 here and 128 there. But now I have two frequency intervals, and the spectrum is a little bit more irregular, the eigenvalues. And those are the corresponding eigenvalues. But again, you see that they're well localized at first, and then they become spread out. But the region over which they become spread out now is broader. Okay? The sharpness of having eigenvalues close to 1 and having eigenvalues close to 0 occurs on a broader set of indices. And that's another example with a larger time frequency area. And those are the corresponding eigenvectors. The thing to take from this picture is simply the fact that you can see that the eigenvectors aren't corresponding to one or the other of the intervals. They're an amalgamation of energy spread over the two intervals in frequency. And here's an example where I took a so-called randomly generated frequency support, and that's what the eigenvalues look like there. And you have this interesting flat region in the middle where you have several eigenvalues of equal to a half. And those are the real parts of the eigenvectors. The spectrum in this particular example is not symmetric about the origin, so I'm just drawing the real parts of the eigenvectors. Okay, and that's the kernel of the operator p sigma qt. So you can see that it's got a band along the diagonal, but then it's got several side bands. And just one more example of a randomly generated frequency set and corresponding eigenvalues. Now the classical result, one version of the classical result of Landau, Lakey, and Pollock, there are several statements of this so-called omega t theorem, and here's probably the easiest one to write down. Is if we fix the frequency supports have length 1, and the time support then is equal to the area, then if we define n of alpha to be the number of eigenvalues of the composition operator greater than alpha, then basically you have the area plus this log term, the product of the logs, one which is the log of the area, and one that depends on alpha, but this term disappears when alpha equals a half, plus big O of log of the area. Okay, so this explains that you basically, the dimension of the space of functions that are essentially time and band limited is equal to the area, plus or minus this logarithmic spreading term. Well, what about multiple intervals? I started asking around a few years ago. Nobody seemed to remember that Landau and Vidon had actually started to consider the multi-interval case. So I'm just going to talk about the case where the time and frequency supports are finite unions of intervals. And in that case, what Landau and Vidon did, they looked at taking the frequency support and dilating it. Okay, so now C, instead of being the area, it's a dilation parameter. And so the corresponding time frequency localization operator is given, well, now you have a family of them depending on these dilations. and you can talk about the number of large eigenvalues of those operators. And what they have then is an asymptotic result that says that again it's the area, but now the eigenvalues, the transition between the eigenvalues being close to 1 and the eigenvalues being close to 0 has a width that now depends on the number of intervals, the number of time intervals and the number of frequency intervals. And that term was a byproduct of how they did things, but they never said in that paper whether that term had to be there or not. Whether the transition from eigenvalues close to 1, eigenvalues close to 0, really depended in an essential way on the number of intervals. So I just want to quickly mention. So this was the picture I showed you before, where you have several eigenvalues close to a half. And of course, this is discrete Fourier transform that I'm using, so things are different in finite dimensions than on the real line. But here's just a heuristic argument of why that transition band depends on the number of intervals. So if you took two functions, if you took several functions phi j that were frequency concentrated on an interval of length 1. So the frequency supports on an interval of length 1. Well, then there's simply modulations of functions that are frequency supported on -1/2 to 1/2. Okay. And if you took two different such intervals and you looked at their time localizations, then their inner product would be simply the integral. So Q is the characteristic multiplication by the characteristic function of -1/2 to 1/2. So you're simply integrating these modulated band-limited functions over -1/2 to 1/2, and you're simply then taking the Fourier transform of this product times the characteristic function of -1/2 to 1/2, which is that, and this is a continuous function supported on -1 to 1, involved with distinct functions. So it decays like 1 over the distance between the centers of the frequencies. So, well, that tells you that if you had several of these, so j and k are 1 and 2 here, but if you had some finite number of them, of functions that were frequency supported on intervals of length 1, and you separated those intervals, those frequency intervals, you set them to infinity at different rates, then each of the intervals will give you an eigenvalue approximately 1/2. So that tells you why in the Landau-Leadom theorem, why you have to have the transition band of length proportional to the number of intervals. Now, if these intervals were very short, then instead of each of them giving you an eigenvalue of approximately 1/2, they would only be able to give you a small eigenvalue. So if your frequency support were very sparse, then you shouldn't have any large eigenvalues, according to this heuristic argument. Now, I'm just going to try to show you an illustration of. Maybe I should do it this way. What happens when you, so here on the top I'm showing the distribution of eigenvalues, and on the bottom I'm showing the frequency support. So I'm going to let it become disconnected, but at the same area. The frequency support is going to have a fixed area, but it's going to become disconnected. So let's look at how the frequency changes. Okay, so what happens is, what you see is that you have this, when you have a symmetric interval around the origin, you have the Landau-Slepian-Pollock situation where you've got several eigenvalues close to 1, the transition, and then eigenvalues close to 0. And what happens is, as the frequency support becomes disconnected, the number of eigenvalues close to 1 gets smaller and smaller, and then you start dragging some of these otherwise smaller eigenvalues up a bit. And if you try generating the frequency support in different ways, you get a similar picture. I think this, yeah, let me try this one. Yeah, this is just a different way of generating the random frequencies, but you see more or less the same thing happening with the frequency supports. Whereas if we generated the frequencies in a more structured way, like that, then something interesting is happening. Now, these are discrete Fourier transforms. Based on what I just told you, if this were happening on the real line, then as the frequency intervals get farther apart, you should be getting few eigenvalues close to 1, and they should be going down. So what's happening? What's happening is well, the fact that you've got a finite Fourier transform means you've got sort of you have these picket fences that also play a role, that also are time frequency localized in a sense as well. And so that's why the spectrum more or less stays the same in that case. So Scott and I, we asked, when is this area formula valid in general? So on the real line, when can we say that we've got the number of eigenvalues we're going to have is proportional to the time frequency here? So Scott looked very closely at Landau's estimates, and he concluded that the correct way of phrasing this, except he got time and frequency backwards, but if you take the frequency support to be minus half to half, and S to be the time support to be a finite union of intervals, it doesn't really matter which is which. But the point here is that what you do is you look at intervals of the form k plus 1, and you count how many of them sit inside of S, or at least some shift of S. And I'm taking the max over all possible shifts. So I'm trying to fit as many intervals of length 1 inside of the time support as I can. And here I'm just counting how many intervals are intersecting S, how many intervals of length 1 are intersecting S. And I'm minimizing that, and then it turns out that the number of eigenvalues of this operator, well, if I look at this number here, that gives me an estimate, a lower bound of a half, the number of eigenvalues we're going to have. And this gives me an upper estimate. Okay. Now, if the set is very disconnected and very random, then these aren't going to be sharp. But if the time support in this case is a shift of a subset that sits on the lattice, then I'm going to get exactly what I want. So I'm shifting back to the time interval of having length 1 and sigma being finite union intervals of the form k to k plus 1, then lambda of the area is exactly equal to a half. Okay. Now there's something else that's going on here. These eigenvalues actually are occurring in pairs when we have something like this. And you can see from looking at a picture that, so here's a half, and these are the eigenvalues bigger than a half, and these are eigenvalues that are less than a half. And if you flip this over, it's symmetrical or anti-symmetrical, and that says that if I go back from the area, if I count eigenvalues backwards from the area and eigenvalues forwards from the area, and I add those two together, I get 1. And that's the frequency support for that picture that I generated. All right, now there are some really fundamental open questions in this area. So this is the analytical stuff gets very tricky. So here's a result from 1993, Donahoe and Stark. If the frequency support has length equal to 1, area has it could be, it doesn't have to be an interval, okay, finite union of intervals, but just a measurable set of measure 1. Okay. And if the time interval is not too big, 0.8, then you've got this inequality, and this is an inequality for rearrangements. This is called the equimeasurable decreasing rearrangement of the Fourier transform. So what I'm looking how much of the energy of F is between minus T over 2 and T over 2 if F is frequency supported in sigma. And what they should is if the measure of sigma is 1 and the time interval is less than or equal to 0.8, then it's best to put all of the energy into an interval centered at some point at the origin sigma. So you're going to get the most energy in this time interval if the frequency support constrained have measure 1 is an interval. Okay. There's every reason to believe that this that the restriction T less than or equal to 0.8 is unnecessary. So there's every reason to believe that it's always going to be the case that you're going to get if a function has Fourier transform living on a set of measure 1, then the most energy you can get in an interval of time t in the time domain is going to occur when the frequency support is an interval. Okay. But that's not a theorem. Okay. For t bigger than or equal to 0.8, it's not a theorem. And in fact, the method that they use, that Donahoe and Stark use, this rearrangement method, it breaks down for larger values of t. So it requires a different method to prove this. Okay. But if anyone knows the solution to this, I'd be extremely interested to hear about it. As far as I know, that's not the problem. So it's known if the time interval is not too big, that sigma should be an interval, but in general it's not. Right. Now, information. So why look at this multiband stuff? Karen Peterson spoke this morning about how in wireless communications sometimes you want to be using multiband. Make use of different ranges of frequency for communications. So I'm just gonna throw this terminology out, and I'm going to say that a time frequency pair supports information if the norm of this time frequency localization operator is bigger than or equal to a half. So it has an eigenvalue bigger than or equal to a half. And I'll say that it supports information at rate n if there are n eigenvalues bigger than or equal to a half. And I'm particularly interested in the case where S is simply a time interval, but the spectrum can be a finite union of intervals. And so I don't know, my knowledge of coding theory is superficial at best, but it seems that the motivation for this should be that you're trying to think of the basis functions that correspond to the time frequency localization operator as giving you an efficient set of codes for transmitting information. So the question is which pairs support information. So you have a trade-off between what part of the spectrum you're able to use with a physical device and how much energy you can get in that part of the spectrum in a finite amount of time. Now there's some deep work on this due to Candes, Romberg, and Tao. They were motivated by problems more similar to what Anna was talking about before in compressive sensing, because they were interested in situations in which you have a signal with sparse frequency support and you only need a small number of time measurements to recover the signal under certain constraints. But I'm thinking of this more in the information theoretic terms that I just mentioned. But their estimate is this: if n is large, so we're talking about finite Fourier transforms here, FFT, that's what we're all here for. And then they have essentially the number of time points plus the number of frequency points. You should think of this as being at most a multiple of n over log n. Then with overwhelming probability, every signal that's frequency supported in sigma has at most half of its energy in S. Okay? So that's in the finite case, this is the same as saying the operator P sigma, Q sub S, P sigma has norm at most a half. So if you randomly generate these sets from a uniform distribution of all subsets of 1 up to n, that's how this problem. But the frequency support is not necessary. And then the question is, how can you start describing which sets sigma support information? Okay. So for example, in terms of entropy.